Hello, and thank you for checking out the Six Sigma Tool Guide. Today we are going to talk about hypothesis testing. We're going to split this up into two videos, probably two 10-minute videos. So this is part one. We're going to talk about how to calculate and use a p-value and a goodness of fit test. So let's go ahead and get started. Okay, so what and why? Why do we use a hypothesis test? Typically it's for validation. It's for validation that the results that you see after your project is complete are, number one, actually causing an increase in performance as hoped, and that it's enough of an increase that it's statistically significant. So we want to answer the question, are the improvements that I made to the process actually contributing to increased performance? And has the process started performing in a significant manner above its old performance? Has it just gone up a tick, or is there a significant change in our results? A lot of folks find themselves at this point in the project after they've completed maybe a pilot program or they've put some solutions in place, and then they're not sure, should I assume that my project was a success, just because I see some level of improvement on my primary metric? We're going to actually measure the improvement on that primary metric and determine whether it's statistically significant or not. And that is the purpose of a hypothesis test. So a hypothesis test. What is a hypothesis? A hypothesis is just a statement. It's simply a statement regarding the new results in a process and what impact your project had on those results. So the null hypothesis states that your project had no meaningful impact on these new results. And if there is some level of improvement, it is probably just random chance and is not really directly related to process changes. Usually the null hypothesis is noted with an H0 by most statisticians and scientists. The alternate hypothesis, this states that your project did have meaningful impact on the new results, and that whatever observed improvements you're seeing in performance is not just random chance, you're not just suddenly having a good month. These are results that are related to some significant change in the process. So usually the alternate hypothesis is noted as an HA, sometimes an H1, depending on who is doing the analysis. But this is the point of a hypothesis test. You hope that you are able to reject the null hypothesis that your project had no meaningful impact, and you want to accept the alternate hypothesis that says that your project did have meaningful impact and that the new results you're seeing are statistically significant. So what are the rules to accepting and rejecting these hypotheses? Well, accepting the null hypothesis, that means that you cannot say with confidence that the new results you're seeing are the result of changes you made to the process. Maybe it's just a fluke, basically. If you reject the null hypothesis, that means that you're at least 95% certain that these new results are not a fluke. This is because of the changes that were made to the process. And when we say at least 95%, we don't mean that as a figure of speech. We're going to actually calculate how certain we are. Scientifically, this decision to accept or reject should only be made by calculating a chi-square off the differences in results before and after your project, and then you approximate a p-value that represents how certain you are. We're going to walk through all of these steps. It is not nearly as complicated as it sounds. There are tons of online statistical calculators. If you go to a trusted source, they're going to be able to help you do it, where you can plug in some numbers and it's going to give you the answer. If you understand how to do it manually first, you're going to have a much easier time interpreting the results you get from a statistical calculator. So that's why we're going to go through the pain of doing it manually, just to get a basic understanding of how it works, and so that you'll be able to interpret results if you use an online statistical calculator. The hypothesis testing we're going to do is for categorical data. We're going to walk through a real-life example that was done here at Transamerica, and it uses categorical data. And when I say categorical data, that means that the results are always going to fall into some predetermined number of categories. If you are doing something with quality scores, where you have a pass-fail rate or a good versus bad result, that's categorical data. If you're doing like customer surveys as your primary metric, and you're looking at categories like very satisfied, satisfied, unsatisfied, very unsatisfied. Those are categorical data points. If you're measuring something like time or money or temperature, things that don't have a specific end, and there isn't a specific number of categories that your results will fall into, you're going to do things slightly differently. We're going to use categorical data in this example. So a p-value, this is basically a probability value. It's a statistical measure that helps scientists understand whether the results of an experiment are within normal range of the values for the events being observed. Said another way, it's really just determining, are these new results I'm seeing a fluke or not? What is the likelihood of this being a fluke? Usually you'll find a p-value on a reference table, but you have to first calculate a chi-square value. We're going to walk through that in a moment. Having a p-value of 0.05 or lower, so 5% or lower, means that you can say with 95% certainty that the new results are due to changes in the process and not just a fluke. P-value will be represented as a percent or decimal point, and this really just represents the probability that the results are random chance or a fluke. Most scientists use 95% as a significance level as the standard. That's a pretty well accepted standard. That's what we'll be using for our projects as well. So, hypothesis testing, we're in 7 easy steps. I'm going to recap them real quick here, and then we'll move on to video 2, where we'll take a closer look at each step. Number 1, you're going to determine your experiment's expected results. That's typically whatever the historical data was prior to the changes you made. So this is the par for the course, normal performance on your primary metric. Number 2 is to determine your observed results. And when we use the term observed results, we're saying what are the new results since the change has happened. Since I removed 3 steps in the process, what is the cycle time now? Or since we completely rearranged the process, how many does it yield now? So this is the new results. You're going to compare those results, the expected results, to the observed results using chi-square. I'm going to walk you through the math on how to do that. You're going to determine your experiment's degrees of freedom. That is a very simple step. It takes about 10 seconds, and I'm going to show you how to do it very quickly. You're going to choose a significance level. We've actually settled already on 95%. That is the measure of how certain we want to be about our results. We're going to use a chi-square distribution table to approximate a p-value. And that p-value is going to decide whether we accept or reject the null hypothesis that our project did not have any meaningful impact. Alright, well thanks for sticking with us so far. If you want to jump over to video 2, we'll go through these steps and get it done.